Okay, starting with part 2 of exponents. You have to be able to move from a fractional exponent to a radical. In other words, if you have a fractional exponent like 7 to the 3/4, you have to be able to change that to a radical. And this is how we do it. So when you look at your fractional exponent, you look at what's in the denominator, and that goes into the root of the radical. The numerator becomes the exponent of the base, and you could take this, flip it up high, and then put parentheses around what's in the radical, just like I did here. All right, so going from here to here, I took this exponent, I moved it out here, and I put parentheses around the entire thing. And the way I like to remember this is roots of trees are below ground. Okay, here's the roots. Okay, so if you think of this as a fraction line here, the root is below the ground, and that goes here. All right, let's look at some other examples. 2 to the 5/3. Okay, you look at the denominator. It's underground. Roots are underground. Therefore, that becomes the root. There's your base. Here's your exponent. You can leave it as is, or you take this exponent, you flip it way out here, and you put parentheses around everything, and there's your exponent. Here's another one. 4 to the 4/3. Here's your root. It's underground. Now, I find it's helpful to draw the symbol first and then put the root in. I find that if you do this first, and then you go to do that, you end up getting this wide, unseemly type of situation. So I like to do the radical symbol first, identify your root, put it out here. Here's your base. The numerator becomes your exponent. You can leave it as is, or put parentheses, and then this goes way up top. Okay, let's go backwards now. If you're given something like this, that's the same thing as or 7. This is your root that goes underneath the fraction line. They are all interchangeable. Okay. Let's talk now. The way to remember that is, all of us pretty much know that x to the 1/2 equals the square root of x. So we know that when we write the square root of x, there's a hidden 2 there and a hidden 1. So therefore, it makes sense that there's your root and it goes in the denominator. Here's your exponent and it goes in the numerator. So if you get a little confused, just remember what we all know, that x to the 1/2 equals the square root of x. Okay, let's talk about multiplying radicals. If you have something like this, because you have the same root, they're both cubed root, you can go ahead and keep the cubed root and multiply what's inside. Okay? Now, if you're asked to simplify this, it's really helpful to switch it back to the fractional exponent. Okay, so here's what's inside, a to the sixth b squared. Here's our root. The root goes underground. Okay, this whole thing is raised to the first power, so that becomes 1/3. Now you use your power rule. So you have a to the sixth times 1/3, b squared times 1/3, and this becomes a squared b to the 2/3 power. And you could even then simplify this to a squared. Take the b, here's your root underground, like so. Let's talk about negative exponents and moving back and forth to radicals. We saw from our last video that when you have a negative exponent, all right, you can convert this in your mind to x over 1 to negative 3 over 2. You take the reciprocal of this. This becomes 1 over x. You change this to a positive exponent, and you apply the power rule. When you apply the power rule, you got to make sure you do it to both numerator and denominator and all your factors. Okay, this becomes 1 over x to the 3/2. Here's your root. It's underground. Draw your radical symbol first. There's your final answer. You could also take this and flip that up, and you could have 1 over square root of x to the 3rd. They mean the same thing. Let's do another one. 5x to the negative 5/4. It's important to pause the video. Try these on your own. This is the same thing as 5x This is 5x over 1 to the negative 5/4. You take this, you flip it, you change the sign to positive. Now you apply your power rule. 1 to the 5/4 is just 1. Here's your root because it's underground. Draw your radical sign first. Important to keep that parentheses. Now if you want, you can flip that up, put parentheses. How about this one? X squared over y, negative 1/3. Flip it, change it to a positive, apply the power rule to numerator and denominator. If you want, you can toss this up and change that to x to the -6th. Okay, sometimes it's helpful to break a fractional exponent into its parts. So this is the same thing as sometimes that's helpful to break this up. Okay, let's talk now about large exponents in the radicand. Okay, so let's say you have something like this. you're asked to simplify that. A nice way to do this is to convert this to a fractional exponent and then apply the power rule. So this is going to be to the 1/3. Okay, here's your root underground corresponding here. There's a presumed 1 as its exponent because this is really that's really what it is. So this 1 goes up here. This is a root. Roots are underground, therefore it's underneath the fraction line. Okay, so now you have x cubed y to the 6th to the 1/3 power. And you know how to handle this. This becomes x to the 3 times a third, which is 1, y to the 6 times a third, which is 2. So your final answer is xy squared. So that is a good way to simplify this, is to convert it to a fractional exponent and apply the power rule. Here's another one. Again, radical sign first, then the root. It's just easier. Convert that to a fractional exponent. We know that this whole thing has a 1. This is your root. Roots go in the denominator. They're underground. Now apply the power rule. Okay, now, sometimes it's helpful to break this up. So we can say that this is a to the 5/5 plus 1/5, b to the 5/5 plus 2/5. Sorry, make that a little neater. Okay. This becomes a to the 5/5 times a to the 1/5 times b to the 5/5 times b to the 2/5. How did we do that? We know that when you multiply with the common base, you add the exponents. You multiply with a common base, you add the exponents. Now, you could simplify this. A to the 5/5 is just a to the 1 times a to the 1/5 power times b to the 1 times b to the 2/5 power. It becomes a times 5th root of a times b times the 5th root b squared, and this becomes a times b times 5th root of a times 5th root of b squared. And be careful, this here has to be with the radical sign. Make sure it doesn't drift over here and your teacher thinks that that is b to the 5th. Another example of using mixed numbers. Two to the 5/4 We could change that to 2 to the 4/4 plus 1/4, 2 to the 4/4 times 2 to the 1/4. Common base, you would add the exponents to get you here. This becomes 2 to the 1st. This becomes the 4th root of 2, 2, 4th root of 2. And again, careful, this 4 goes with the root. This is not 2 to the 4th times the square root of 2. This is 2 times the 4th root of 2. Okay, let's see. Could we have done that another way? Let's take this, bring it down here. Convert it to a radical. The root is underground. There's your root 2 to the 5th power. Okay, we could change this to 4th root 2 to the 4th times 2 first. We could change that to 4th root of 2 times 4th root of 2 to the 1st. Okay, remember, when you have the same root and you're multiplying, you keep the root the same and multiply what's in the square roots. Okay, now let's take this and take that back to a fractional exponent. Here's our root. That's going to go in the denominator. Here's our exponent. This becomes 2 to the 1st times the 4th root of 2, or 2 times the 4th root of 2. Same answer. This way, same answer. Okay, different ways to do this. So let's review how we did this. We took this 5/4, we broke it up into 4/4 plus 1/4. We recognized that this is the result of this multiplication. We changed 2 to the 4/4 to 2 to the 1st. Here we convert it back to a radical. Our root is under the denominator sign. There's a 1 there, which corresponds to the numerator. It's our final answer. Careful, don't let this root drift over here. Keep it with the radical sign. This is not 2 to the 4th times square root of 2. Another way to do it, convert it to a radical. Here's our root. It's under the fraction line. We change 2 to the 5th into 2 to the 4th times 2 to the 1st. This is the same as the 4th root of 2 to the 4th times the 4th root of 2 to the 1st. We convert this to a fractional exponent. This is our root. The root goes in the denominator. Here's our exponent. It goes in the numerator. This becomes 2 to the 1st, and you get your same answer. Okay, one thing we need to talk about is extraneous solutions. Let's see if I have that. Extraneous solutions have to do with the fact that when you raise a function to an even exponent, okay, classically you're going to square it. When you do that, you have to be careful because you're going to introduce extraneous solutions. So you always have to check your answers when you are squaring or raising something to an even power to solve an equation. Okay, here's an example. Let's say you're presented with this equation and you're asked to solve it. Square root of x plus 6 equals 2x. Okay? You know you're going to end up wanting to square both sides to get rid of that radical. All right, so let's first move everything to the opposite side. So you'll have the square root of x equals 2x minus 6. I'm sorry, this should be an x. Okay, so at this point, we square both sides. All right, this, as we've learned, is x to the 1/2 equals 2x minus 6. Okay, we raise both sides of the equation to the second power, like so. We apply the power rule here, and we get x equals 2x minus 6 squared. All right. We go ahead and we expand that. So x is going to equal 4x squared minus 24x plus 36. Okay. We solve that using the quadratic equation. Okay. I don't want to do it in the interest of time. You end up with 25 plus or minus 7 over 8. And you end up with 4 and 18 over 8. Here's the problem. Whenever you raise something to an even power during the process of solving for x, you have to check your solutions in the original equation. Okay, you cannot plug it into this equation, which occurs after you squared both sides. You have to plug these all the way back up into the original equation. And you'll find that on occasion, you have introduced an extraneous solution. Okay, so let's plug both of these in. You have, let's try 4 first. So the original equation is the square root of x plus 6 equals 2x. So you're going to have the square root of 4 plus 6 equals 2 times 4. You're going to have 2 plus 6 equals 2 times 4, 8 equals 8. This is a legitimate solution. Now, let's plug in this one. We're going to have square root of 18 over 8 plus 6 equals 2 times 18 over 8. You are going to have, this ends up being the square root of 2.25 plus 6 equals 2 times 2.25. In other words, 18 over 8 equals 2.25. You're going to have square root of 2.25 equals, this is 4.5. I'm going to take this and put it on the other side of the equation. Okay, this is not true. It's not a true statement. How do I know that? Because this has to be positive. You can't get a negative number there, and here's a negative number. So there's no way that these two sides of the equation are equal, which means this is an extraneous solution. Okay, in the next video, I will review the worksheet, don't forget, when you square both sides of an equation, you have to check your answer. And the way I remember this is, even though it applies to any even power, I think about square dancing. Okay, when you're square dancing, not that I've done a lot of it, all right, you got people moving around. I think there was something called do-si-do, and you're square dancing and spinning around and grabbing hands and moving. And periodically, when you're square dancing, you have to check to make sure you're still with the same partner. So that's how I remember it. When you square dance, you have to check that you're still with the same partner and someone else didn't gravitate towards you or vice versa. When you square both sides, you check your answer. Just like when you square dance, you check your partner.